The suggestion was made that I should separate the theory and how we do things from the examples. So this is version number 2 of the chain rule. We're going to learn how to derive the chain rule and how to use the chain rule to find derivatives of compositions of functions. First, we're going to break apart compositions of functions. As a quick refresher, a composition of functions is when one function is inside of another function. We're going to start building and then we'll break things apart. If you wanted to put these two things together, you could write y is equal to sine of x squared. If you came upon sine of x squared, you should realize, hey, I don't know how to do that derivative yet. You might know the derivative of sine, and you might know the derivative of x squared, but this isn't sine multiplied by x squared. You wouldn't use the product rule. This is x squared inside of sine. Let's try composing another set of functions. Well, same functions in a different order. So what function do you put inside of what? Y is equal to something squared. That something is sine of x. Now here, you could find the derivative of sine of x squared using the product rule if you rewrote it as sine of x times sine of x. But we're here to give you options on how to find derivatives. If you were given y equals cosine cubed of x and you had to use the chain rule, we'll get there eventually. What you need to see is that this is two functions, a cosine function and a cubing function, and one is inside of the other. The outer function is something cubed, and the inner function is cosine. So what we do is we call that inner function cosine, which means that outer function we can think of now as u cubed. Why will that help? Because those two pieces are very easy to take the derivative of. You should be able to take the derivative of u cubed, and you should be able to take the derivative of cosine. We'll come back to these examples in a moment. We're going to break apart some more functions. This should be easier to tell what's the inner function, what's the outer function. The outer function is cosine, so we're going to rewrite this as y is cosine of u, which makes u equal to sine of x. Let's keep practicing this inner-outer function stuff. Can you tell what the inner function is? Well, the outer function is cosine, so we'll rewrite y is cosine of u, and the inner function is for x squared. One more time, this is something you could use the product rule for, but most of us don't want to multiply out 2x minus 7 3 times. We don't want to do binomial expansion, so we can think of this as something cubed, and the something that's being cubed is 2x minus 7. Oh, looks like we have one more to pull apart, maybe more than that. We're going to rewrite this as 3 sine of something. We call that something u. U is 2x cubed. Okay, so now we're going to go back through all of those same pieces. You'll get a chance to break them apart again. And we're going to do the derivative this time, showing you how the chain rule works. When you're done with the derivative of y equals cosine cubed of x, you're going to have dy over dx is equal to something. You might be thinking, why not y prime? You'll see in a moment that y prime notation loses a little bit of meaning compared to this dy over dx notation. So first we're going to break this apart, inner and outer functions. The outer function is the cubing function, so we'll say y is u cubed, and u is equal to cosine of x. So the derivative of u cubed is very easy, 3u squared. But we're not going to write y prime, we're going to write d something over d something. Definitely dy, but not dx. The input was not x, the input was a u. So dy du is 3u squared. The derivative of cosine of x is negative sine of x. And we're going to use d something over d something. What's that going to be? du over dx. So when we're using the chain rule, we're breaking things apart so we have easier derivatives. Let's see what happens when we put things back together. Remember, we want dy dx. However, we only have dy du and du dx. Hopefully you see that du over du, those can actually divide, and we end up with dy over dx. Well, so now right here we need to write what dy over du is equal to. That's 3u squared. And we need to multiply that by what du over dx is equal to. That's negative sine of x. So dy over du, 3u squared, multiplied by du over dx, negative sine x, should give us dy dx. Now I'm going to change this back in a moment. For right now, I'll write 3u squared. I'll put the negative out front so I can just write sine of x here. But you shouldn't be expecting the derivative of cosine cubed to have a u in it. So instead of that, what can we square? What's u equal to? Up top, u is equal to cosine of x. So instead of u squared, we will write cosine squared x. It's a lot of work for now, but we're going to practice all of the work so that in the future, we can write less and we know what we're skipping. Okay, there's no way we could break this apart. This is not multiplication. Cosine of sine of x is sine inside of cosine. So we're going to say u is cosine of x. That's the wrong place for u. Sorry. We're not going to say u is cosine of x. We're going to say y is cosine of u, and u is equal to sine of x. dy du is negative cosine, nope it's not, negative sine of u. du dx, the derivative of sine with respect to x, is cosine of x. I'm going to write this in a slightly different order. I know I'm going to be multiplying dy over du times du over dx. So I'm going to write dy over du on the left-hand side of the equal sign, and on the right-hand side I will write what dy over du is equal to. Multiplied by du over dx on the left, and multiplied by another version of du over dx, cosine of x. The du's divide, and we're left with dy over du, nope, dy over dx, is equal to negative sine of, we're going to leave that blank, fill in the u, multiplied by cosine of x. What's the input to sine? Instead of u, we are going to write what u is equal to sine of x. That's a weird answer, but the derivative of cosine of sine of x is negative sine of x multiplied by cosine of x. Maybe I'll put a little multiplication thing here. Hopefully you're getting better at recognizing the outermost function. So y is going to be cosine of u, while u is 4x squared. dy du is going to be the derivative of cosine, that's negative sine of u, and du dx, that's 8x. So dy over du, which is negative sine of u, multiplied by du over dx, cross off those du's, they divide to 1, multiplied by 8x, and we will get dy over dx is equal to negative 8x, I'm just rearranging, multiplied by sine of, let's not write u, we're going to write 4x squared in place of u. We're still going to do these the long way. I'm going to add another video that shows the shorter version once we understand the longer version of the chain rule. What's the outer function here? Weirdly, some people find this tricky. The outer function is the cubing function. So we'll say, why is something cubed? This something being cubed is 2x minus 7. dy du is 3u squared. du dx is equal to 2. So dy du multiplied by du dx, divide out the du's, is 3 times something squared times 2. Let's see, that was u squared. We'll replace u with what u is equal to, 2x minus 7. And just make everything pretty. dy dx is 6 times the quantity 2x minus 7 squared. If you're ready for a little treat at the end, let's look at this one. So in the future, we're going to give you some super complicated things. What's the outermost function? Well, that's the cubing function. So we can say y is equal to u cubed. And u is equal to secant of 2x minus 5. Hopefully you're thinking right now, well, secant of 2x minus 5, that's got a function, secant, with an input of another function, 2x minus 5. That means we actually have to use the chain rule twice. So instead of a 2x minus 5, we're going to put another variable in here. We can't use u, so we'll use the next letter in line, v. And v is equal to 2x minus 5. So when we're done, we should have dy dx is equal to a whole bunch of, I don't know, secants, cosecants, and tangents of 2x minus 5. I'm going to show you how to do this, but I'll let you finish it for yourself. The process is the same as when we had one function inside of another. We just take the derivative of each of these functions separately with respect to their input variables. So dy d, that's right, u is 3u squared. And then here in the middle, it's going to be du over d, v. And the derivative of secant of v is secant v tangent v. One more derivative to go. What's the last one? dv. Now we finally get our dx. And that dv dx is a very easy 2. Do you have it? What are we going to do next? We're going to multiply dy du by du dv multiplied by dv dx, and the dv's divide to be 1, the du's divide to be 1, and we would get dy dx. I'll let you work out what to do on the right-hand side, and don't forget, you're going to have to resubstitute. If you have u's and v's at the end, you're not at the end yet. Thanks for watching.